Let's look at this problem. We have a short horizontal link, this one. Let's call this point O. So AO is pinned at point O. Therefore, AO is doing rotation with a fixed axis, about a fixed axis. And then AO is connected to rod AB, and then AB is connected to a block here at point B. This block can only move in a horizontal fashion inside this slot. And we need to determine the linear velocity and linear acceleration of this block at this moment when the angular velocity and angular acceleration of link AO are given. So we know that this block will have the same linear velocity and linear acceleration as the point B right here. So we're actually looking for VB as well as AB. And then if we apply the relative motion analysis, we will need to know the linear velocity and acceleration of another point on the same rigid body. So in this case, that point will be point A. Even though right now we do not know that about point A, but we know that point A also belongs to another rigid body, which is AO, and we can determine the linear velocity of and acceleration of point A from this link AO. So because AO is doing rotation about a fixed axis, so actually that makes things a lot easier. We know that the velocity of point A must be vertical down because the path is going to be a circular path. Therefore, VA has to be tangent to that circular path and perpendicular to this radius. Therefore, if we set up our conventional XY coordinate system this way, then we know that VA must be vertical down. So VA vector equals to negative. The magnitude is determined by omega. So VA equals to omega AO times the radius RA, both in scalar. So that will be 4 times 0.5 along the J direction. So that equals to negative 2J in the unit of meter per second. So that's VA. What about AA? So for AA, it has two components. One is tangential AT, which equals to alpha R. The other one is normal AN, which equals to omega squared R. So AT is along negative J direction and AN is along positive X. So positive I has a positive I unit vector for its direction. Therefore, AA equals to omega squared times R. So that will be 4 squared times 0.5 along positive I direction. And then AT negative J minus alpha is 8. R is 0.5J. So that equals to 8I minus 4J in the unit of meter per second squared. So now we have determined the linear velocity and linear acceleration of point A because point A belongs to the short link AO. Now recognize that point A also belongs to the rod AB. We can write relative motion analysis for linear velocity and acceleration to determine the linear velocity of point B and linear acceleration of point B, because AB also belongs to the same rigid body. So now VB, even though we do not know the magnitude of VB, we do know the direction. The direction must be horizontal, so the component must be I. There's not going to be any J component, and that equals to VA plus omega AB, the angular velocity of the rod AB, and then cross vector RB relative to A. VA is given, negative 2J, not given, it's determined here. Omega AB is not known, but we know that doesn't matter what the magnitude is, the direction must have the k component cross RBA. Now RBA is this vector right here from A to B that has horizontal components along the negative x direction of, that's negative 2 cosine 30 degree I, and then the vertical down, so along the negative y direction with a component of 2 sine 30 degree j. Therefore, let me move it over here, VBI equals to, after we have evaluated everything, negative 2j minus 1.732 omega AB j plus omega AB I. Because k cross I equals to positive j, but we also have a negative sign here, k cross j equals to negative I, but we have another negative here, so negative cancel out. So that's what it is. From here, we can separate this vector equation into two scalar equations, one along the I direction. So along the I direction, on the left hand side, we only have VB. On the right hand side, we have only omega AB. And then along the J direction, we will have on the left hand side 0. On the right hand side, the components will be negative 2 minus 1.732 omega AB. So from here, we can solve for omega AB first from the second equation, and that equals to negative 1.15 radian per second. Negative sign shows that the rotation is clockwise. At the same time, well, not at the same time, because VB equals to omega AB, VB also equals to negative 1.15 in the unit of meter per second. So negative because it's pointing towards the left x direction, negative x direction. So that's the first step. At this point, again, I want to mention that if you know instantaneous center of zero velocity, you can again solve this problem, at least this part, relatively easily, because we know the direction of linear velocity of point A, and we know the direction of linear velocity at point B. Therefore, if you extend these two lines and then you draw two other lines that are perpendicular to each one of them, where they intersect, this is the instantaneous center of zero velocity. And this distance right here is RA with respect to IC, and that equals to 1.732 meter, which is 2 times cosine 30 degree. This right here equals to RB relative to IC, which equals to 1 meter. Therefore, VA equals to, from the previous step 2, we're using scalar only, and that equals to omega AB RA relative to IC, which equals to omega AB times 1.732. So from here, you can solve for omega AB to be 2 divided by 1.732, which is also 1.15 radian per second. And then because VA is in this direction, and then VB is in this direction, you can tell that the rotation is clockwise anyway, so you manually determine that the rotation is clockwise. And then VB will equals to omega AB times RB relative to IC, which is 1.15 times 1, which again equals to 1.15 meter per second. And then you can just manually determine the direction of that velocity. So you can use the method of instantaneous center of zero velocity to determine to solve this half of the problem relatively easily. So I'm just showing you this again, this alternative method as comparison, and you will get exactly the same results. So moving on to the second half. For the second half, there's no real instantaneous center of zero acceleration, so there's no shortcut for the second half. we are going to again write the equation using the relative motion analysis. So AB, again, we know the direction has to be horizontal, has to be along the x direction. So AB only have the component of the I direction. That equals to A vector plus alpha AB vector cross R B relative to A minus omega AB squared R B relative to A. So this equals to 8I minus 4J determined earlier plus alpha AB, we don't know what it is, but the magnitude, sorry, the direction is K direction, cross, same RAB from the previous step, negative 2 times cosine 30 degree. So that's basically just square root of 3 minus 2 times sine 30 degree, that is just 1. Okay, and then don't forget minus omega AB squared. Omega AB has been determined to be negative 1.15 squared, and then the relative position again, negative square root of 3I minus 1J. Okay, so now that is 8I minus 4J, and then similar to over here, negative 1.732 alpha AB J plus alpha AB I, similar to this part right here, and then negative sign cancel out, plus 2.309 I plus 1.333 J. So again, we have a vector equation, and we are going to separate that into two scalar equations, one for the I component. For the I component, on the left hand side we only have AB, on the right hand side we have 8, and then plus alpha AB, and then plus 2.309. For the J component, on the left hand side we have 0, on the right hand side negative 4, negative 1.732 alpha AB plus 1.333. So again, two equations, two unknowns, alpha AB and AB. So from the second equation, we can solve for alpha AB to be negative 1.54 radian per second squared. Negative sign indicates clockwise rotation. And then substitute that into the first equation, we can solve for AB to be 8.77 meter per second squared to the right. So now we have solved this problem.